Hello, my name is Scott Chiseco, and I'm a scientist at the University of California at Santa Barbara. Thank you to Drs. Mukherjee, Areli, Bhattacharya, Vilhoth McDonald, and Sathray for hosting us here today. I'll be talking about global groundwater wells, and this is some work that I've been completing for 5-6 years with Dr. Deborah Perrone, who is also a professor here at the University of California at Santa Barbara. So the main findings of our research project are the following. 1. 6 to 20% of global wells are not too much deeper than the water table, implying that many wells are vulnerable to running dry with only modest groundwater level declines. Our second main finding is that there are some places where water levels are declining, and yet newer wells are not being drilled deeper than older wells. In these places, the new wells are just as vulnerable to running dry as the older wells should groundwater levels decline. So in 2015, Dr. Deborah Perrone and I asked the following question: how deep are typical wells? We couldn't readily answer this at the time because we were unaware of any database of global wells, so we set out to look for global well drilling data. We started in the United States, and we contacted 64 different agencies asking for their permission to access well completion records. We sent surveys to database managers to learn more about the data we were analyzing, and in each case we kept close track of any biases in the datasets or any shortcomings in the datasets. The total compilation for America involves 12 million groundwater well completion records. This is a map showing the reason that wells have been completed in the US. Blue dots are domestic and municipal wells, green are agricultural wells, and red are wells used to support industries. We also constructed maps of the depth of wells. Dark blue are deep wells, and light blue are shallow wells. These data provide locally relevant information nearly everywhere that groundwater is used, and this information provides insights into water demands and geologic conditions. But our analysis of only the United States of America was unsatisfying, so we began looking for publicly available groundwater well construction data elsewhere. Over the past 5 years, we compiled 134 groundwater well completion databases. These datasets span 40 countries, and the 40 countries encompass about half of global groundwater pumping. We compiled a database that includes 40 million wells, and these well completion records provide insights into the depth of wells. We have locally relevant information about hydrogeology and groundwater demands in many areas. For example, these maps display groundwater well depths. Deep wells are red, shallow wells are blue. So this 6-year effort allowed Deborah and I to answer the question, how deep are wells, at least for the 40 countries for which we were able to identify publicly available data. The resulting frequency plot demonstrates the range of well depths among the 40 countries that we analyzed. Blue bars show the prevalence of shallower wells, and orange and red shades show the prevalence of deeper wells. The median well is about 30 meters deep. The great majority of wells are shallower than 100 meters, but there's a wide range. The 5th to 95th percentile range is 4 meters to 130 meters, so immense spatial and, as we'll see in a minute, temporal variation in groundwater well completion depths. So this data set allowed us to address the question, how deep are wells, but perhaps the most important question when it comes to wells is, where might they run dry? So we next tried to address this question by examining vertical offsets between the water table and the well bottom. So wells that are relatively shallow, such as the one depicted here, might not tap depths that are all that much deeper than the water table itself. And if nearby wells begin to, say, increase pumping and lead to concomitant water table declines, it's not impossible that shallower wells may run dry. And in fact, we know that the problem of wells running dry is here and now. This is a database of self-reported events where a well has run dry in the state of California, in the western part of the United States of America. And in this location, thousands of wells have run dry in the past decade alone, as depicted by the yellow dots on this map. So we wanted to take a look at the prevalence of wells that are either have run dry or may run dry at a global scale. And we did so by comparing the well depth data that we've put together in our compilation. That's shown on the 4 maps on the left-hand side. Red wells are deep, blue wells are shallow. We then compared the depths of wells to the depth to the water table, starting with 2 global estimates based on hydrologic models, and then I'll show in a minute that we also have put together some observation-based estimates. The upshot and ramification are as follows. 6 to 20% of wells are less than 5 meters deeper than the water table itself. Our finding implies that many wells are at risk of running dry if the water table declines by just a few meters. We identify similar patterns for California's Central Valley, and this is an observation-based approach developed on water level data, so real-world measurements of water levels. And we get a similar answer to what we see with some of the global model results. So one straightforward question that someone might ask is, are wells being constructed deeper in these places where wells are running dry? To address this question, we began looking not only at the spatial patterns of well depths, but also examining how groundwater well completion records have changed over time. So on this particular plot, each point is a newly constructed well. The y-axis value represents the depth of each new well. For example, the well depicted in purple is about 130 meters deep, and the x-axis values provide the well completion date. So for this particular area, wells are being drilled deeper over time. And in fact, if we examine the United States of America as the whole and plot the rank transforms of well completion date and well depth and the statistical relationship between those two, depicted by a rank correlation coefficient, we tend to find that red areas, which represent places where wells are being drilled deeper over time, outnumber blue areas where wells are being constructed to shallower depths over time. This map depicts the time interval 1950 to 1975. We can examine other time intervals too. If we zoom ahead to 1975 to 2000, again, the same pattern, more red than blue, implying that newer wells are deeper than older wells in most places. Likewise, in more recent years, 2000 to 2015, now more expansive time intervals, 1975 to 2015, and last but not least, 1950 to 2015. All in all, we tend to find that wells are being constructed deeper over time in the vast majority of areas across the United States. And our finding isn't just important to the United States of America. If we look to other countries such as Australia, again, red areas represent places where newer wells tend to be deeper than older wells. This drilling deeper trend is prevalent in Australia, Brazil, Canada, Chile, France, Japan, Mexico, New Zealand, South Africa, Sweden, and many other of the 40 countries for which we had data. Our overall finding is that newer wells are often, but not always, deeper than older wells. But what we really want to know, if we want to understand if newer wells are more resilient than older wells to running dry, is, are wells being drilled deeper over time in places where groundwater levels are declining? So what we did was we compared groundwater level time series from monitoring wells against groundwater well completion depths to address the question, are wells being drilled to deeper depths where groundwater levels are declining? Here's a monitoring well time series. The top of the blue shaded area represents the observed groundwater level over time. For this particular area near Stockton, California, groundwater levels have declined at a rate of about 3 meters per decade. Now, if we overlay the groundwater well construction vents, depicted in yellow here, close to the monitoring well, within about 5 kilometers of the monitoring well, what we see is that these groundwater wells are being constructed deeper at a rate of about 7 meters per decade. So newer wells are deeper than older wells at a pace that is roughly twice that groundwater levels are declining. Now, this might be hinting at risk aversion of groundwater users in the area. Drilling deep wells in this area is possible. On the right-hand side, a highly simplified lithological log shows that coarse-grained materials exist to deep depths. enabling deep wells to pump fresh water at high rates. So the answer to the question, how are groundwater users reacting when groundwater levels decline, for this particular area is the following. Those who can afford to drill deeper wells. But I want to emphasize those who can afford. Drilling a new domestic well in California costs thousands, if not tens of thousands of dollars. Drilling a new irrigation well can cost hundreds of thousands of dollars. And drilling a municipal well can be $1 million. Finances are a major issue. People don't have the money to drill the new wells, and that's the biggest problem. This is a quote from a groundwater user in the area whose well ran dry. Let's examine one more area before zooming back out to the globe. Portales, New Mexico is located in the south-central United States on the fringes of the southern portion of the High Plains Aquifer System. Here's a monitoring well from nearby Portales, New Mexico. The observations demonstrate that groundwater levels are declining at a rate of about 3 meters per decade. And if we examine the groundwater well drilling patterns, depicted as yellow points, near the monitoring well, what we find, unlike the case near Stockton, California, is that newer wells are not much deeper than older wells. Now, one reason that the newer wells are not much deeper than the older wells in this area is that a low permeability layer exists at relatively shallow depths, 50 meters below the land surface, maybe even shallower than that. And this renders the strategy of drilling deep wells unhelpful. Here's a quote from a consultant report in the area. Deep groundwater is of low quality and also of low quantity. Said another way, wells in this area are already at the practical bottom of the aquifer. Groundwater levels are declining, and there's nowhere to go. So at a global scale, we began compiling monitoring well data. Among the countries for which we could find publicly available resources, we downloaded monitoring well databases, and in some, the compiled data represent about 1 million unique monitoring wells, and within those 1 million monitoring wells, there's about 100 million water level measurements. These data allow us to identify places where well water level observations demonstrate groundwater level declines. The red areas on these particular continental scale maps demonstrate areas where groundwater levels have declined in recent decades. So armed with both our monitoring well database and then also our groundwater well completion database, we can compare monitoring wells and well drilling events, and what we find is that newer wells are not deeper than older wells in some of the areas where groundwater levels are declining, just like we saw in eastern New Mexico. So the main finding here is that newer wells are at least as vulnerable as the older wells are to running dry, should groundwater levels continue to decline. And thus the main takeaways of this project. Across many important aquifer systems around the globe, wells are at risk of running dry because, 1, millions of wells are not much deeper than the water table itself, implying these wells are at risk of running dry with only modest groundwater level declines. And 2, because newer wells are not being constructed deeper than older wells in some of the areas that are already experiencing groundwater depletion. Thank you very much for attending today, and I'm looking forward to engaging in the questions and answers.